Relating moles to coefficients in a chemical equation. I, Mr. B. Pre-lab discussion. The mole is defined as Avogadro's number, 6.02 times 10 to the 23 particles. These particles may be atoms, molecules, formula units, ions, electrons, etc. The concept of the mole is very important, especially when dealing with quantitative studies of chemical reactions. When calculating quantities of solids or liquids, molar masses are used. The molar mass of a substance is the mass in grams of 1 mole of particles of that substance. When calculating quantities of gases, molar volumes are used. The molar volume is the volume occupied by 1 mole of a gas at STP. Chemical reactions are represented by balanced chemical equations. Proper interpretation of an equation provides a great deal of information about the reaction it represents and about the substance involved in the reaction. For example, the coefficients in a balanced equation indicate the number of moles of each substance. Thus, the ratio of moles of the substance to moles of any other substance in the reaction can be determined at a glance. In this experiment, iron filings will be added to an aqueous solution of copper 2 sulfate. A single replacement reaction will take place, the products being iron 2 sulfate and copper metal. The balanced equation for this reaction is solid iron plus aqueous copper 2 sulfate will form aqueous iron 2 sulfate and copper metal. The quantities of iron and copper sulfate used as reactants will be such that the copper sulfate will be in excess. Thus, the iron will be the limiting factor in determining the number of moles, gram atoms, of product that will be formed. As the equation shows, the number of moles of copper produced should equal the number of moles of iron reacted. This experiment should aid in the understanding of balanced equations and single replacement reactions. The purpose is to find the ratio of moles of reactant to moles of product in a chemical reaction. Relate this ratio to the coefficients of these substances in the balanced equation for the reaction. The equipment will be a balance, a burner, a 100 milliliter beaker, a 250 milliliter beaker, a 100 milliliter graduated cylinder, a ring stand, iron ring, wire gauze, glass stirring rod, safety goggles, and a lab apron or coat. Now for the procedure. Find the mass of a clean, dry 100 ml beaker. Record this as A in your data table. The mass of a 100 ml beaker is 69.01 grams. Now measure out 8 grams of copper sulfate crystals, CuSO4, and add these to the beaker. I have my 8 grams of copper sulfate that I measured out previously. I'm going to add that to the beaker. Now measure out 50 mLs of water in a graduated cylinder and add it to the crystals in the beaker. Have my 50 mLs of H2O here. I'm going to add it to the crystals in the beaker. Now, while a lab partner continues with step 4 and 5, The other should carry out the instructions in step 6. So step 4 says set up the apparatus as shown in figure 15-1. That's figure 15-1. Now we're to heat the mixture in the beaker to just below boiling. Do not allow the liquid to boil. So I'm now going to heat the mixture. Until just below the boiling point of water. Continue heating and stir the mixture until the crystals are completely dissolved. This may take a while because copper sulfate crystals are soluble in water, but it takes a while to dissolve the crystals. Remember also that the blue compound, the copper sulfate that I'm dissolving, is called copper 2 sulfate pentahydrate. That means that for every molecule of copper sulfate is associated with 5 molecules of water. The copper sulfate has almost all dissolved. And the water is not boiling, which is good. All right, all my copper sulfate has now dissolved. Using the balance, measure out precisely 2.24 grams of iron filings. Remember, do not place any reagent on the balance pan. Record the mass as B in the data table. Well, I've already measured out my iron filings. This is actually 2.24 grams of iron filings. Add the iron filings, small amounts at a time, to the hot copper sulfate solution. And you see that we got a little reaction going on here where more bubbles are being formed. This represents what's called a single replacement reaction. A single replacement reaction where the iron that I added to the solution is now exchanging with the copper 2 cations that are in solution, producing aqueous, iron 3 sulfate, and copper metal. Add a little more iron to the allow the beaker to sit for about 10 minutes while the reaction proceeds. Record your observations as D in the data table. Well, my observations are that the solution became less blue. And I'm getting a red, so less blue, and a red precipitate is forming. That red precipitate is actually the copper that was displaced by the iron in copper 2 sulfate. The reason the solution became less blue is because when copper compounds are dissolved in water, they make a blue solution. Okay, it's been about 10 minutes and the solution is really green now. It's like a light green color. It's like a light green color. We see our copper has been displaced and formed at the bottom of the beaker. I think the reaction has completed because no more bubbles are being formed. You can see the copper right here. Remember, the copper was initially contained in copper 2 sulfate. Now the copper has been displaced and the compound is now dissolved in solution. It's called iron 2 sulfate. So the solution contains a compound made of iron because the iron displaced the copper in copper 2 sulfate. Now we're supposed to decant. Decanting means pouring the liquid off of the precipitate in the beaker. So to decant, I'm now going to hold the stirring rod and pour the liquid off the precipitate, trying to preserve as much of the precipitate as possible. Okay, so now you see we have copper formed there. Okay, the next step is to add about 10 mLs of water to the solid in the 100 ml beaker. Stir vigorously in order to wash off the solid. So add 10 mLs. About 10 mLs right there. Pour it into the beaker. And now I've got to let the solid settle out, and I've got to decant the liquid. And then I'm supposed to repeat the washing. So you can see the copper has settled out of the liquid already. Now I'm going to decant again. Okay. Okay. Now I've decanted again. Now I'm supposed to spread the solid out on the bottom of the beaker and place the beaker in a drawer or an oven to dry. I actually have a drying oven here, so I'm going to do that. And then it says complete step 11 and the rest of the experiment at the beginning of the next lab period. Then I'm to find the mass of the beaker and the dry copper metal, record this as C in the data table. So now I have to let this dry, and I'll come back. After drying the sample, it looks like this, where you can see the powder on the bottom of the beaker is red, meaning that it is copper. Now I have to find the mass of the beaker and the dry copper metal, record this as C in the data table. So I'm going to record the mass of the beaker and the dry copper. And the mass of the beaker plus the dry copper is 71.57 grams. Now I simply must complete the calculations. Observations and data. A. The mass of the beaker. The mass of the beaker was 69.01 grams. The mass of the iron filings was 2.24 grams. The mass of the beaker plus copper was 71.57 grams. And the visual observation is a red precipitate formed and the solution became less blue. Now for the calculations. Find the mass of copper produced, C minus A. C minus A is equal to 71.57 grams minus 69.01 grams. This equals 2.56 grams. Now find the number of moles of copper produced. 2.56 grams divided by 64 grams per mole is equal to 0.04 mole. Remember, 2.56 was the mass of the copper from calculation 1. Find the number of moles of iron reacted. That's 2.24, the initial mass of iron, divided by 56. This equals to 0.04 mole. And finding the whole number ratio of gram atoms of iron to gram atoms of copper, the molar ratio is 1:1. Conclusions and questions. How does the ratio found in calculation 4 compare to the ratio of coefficients of the same metals in the balanced chemical equation? The ratio is 1:1 in our calculations and in the balanced equation. How many moles, grams, atoms of copper sulfate were used to produce a solution in the experiment? We used 8 grams of copper sulfate. 8 divided by 1/6 is equal to 0.05 moles. Why is this amount excess? Because it should be 0.04 moles. It should be a 1:1 ratio. According to the balanced equation, the ratio of iron to copper sulfate should be 1:1. But here it is 1 to 1.25, meaning that copper sulfate is in excess. Explain why the iron is a limiting factor in the experiment. Well, all the iron was used up. That's why it's limiting. A general description of the single replacement reaction in this experiment is a metal plus a salt in solution yields a new metal plus a new salt solution. Give a balanced equation for another example of this type of single replacement reaction. Well, that would be Na plus AgCl yields NaCl plus Ag. Consider the reaction Cu plus 2AgNO3 yields 2Ag plus CuNO3 aqueous. If 3 moles of copper metal reacts, how many moles of silver metal will be produced? In this calculation we write 3 moles of copper times a fraction, 2 moles of silver divided by 1 mole of copper. This will give us 6 moles of silver.